All right, last one. So this time we're going to be looking at some problems that have inclined planes. Again, no new concepts, just trying to break up the homework so it's not a zillion problems all at once. All right, so in this first example, we've got this inclined plane. All right, and we've got these two blocks here. It tells us that the two blocks have the same mass. And so we're allowed to change the angle of the ramp is angled at. That was a bad sentence. And we need to find the maximum and minimum accelerations the system could experience. So let's kind of run through the different possibilities. So I guess at the most extreme, theta could be 90 degrees, right? I need to calibrate my board. All right, so if theta is 90 degrees, basically what we end up with is a ramp that is completely vertical with a pulley at the top, and then a box hanging over each end. And if the two boxes are equal, then we're going to have force of gravity over here, which is mg. We're going to have force of gravity over here, mg. You know, one of them has to be negative. You end up with an acceleration of 0, right? Okay, so I think that's probably the smallest acceleration you could get would be 0, right? Because the sign is somewhat arbitrary, right? All right, so what happens if the angle is smaller? Well, if theta is 0 degrees, then, here, we'll do this in blue. Theta equals 0 degrees. Well, then your system looks like this, right? You're going to have your mass with the pulley and your mass. I'm using m to represent both masses since they're equal, right? And so our force of gravity is just going to be mg. And then, yeah, well, let's make this way positive, right? Since it's clearly going to accelerate that way. So now, if I look at my whole system, for my system, I end up with net force equals net force. So the mass of my whole system is 2m. That's equal to my net force, which is just mg. Oh man, fail. Net force is mass times acceleration equals my total force, which is just mg, right? So divide both sides by m, and you find a is g over 2. So 4.9 meters per second squared, right? All right, and then I guess technically you could make your angle a negative angle, right? So what's the smallest angle we could have? I guess negative 90 degrees, right? And then you would just have a ramp like this with your two blocks on it, and it would just be falling straight down, right? And so in that case, your acceleration would be negative 9.8 meters per second squared, right? Okay. All right, so that is that. When I originally wrote the problem, this was the answer I was looking for, though. But I guess technically that it could be a negative angle. All right, so let's do part 2. It says if we assume the ramp is frictionless, what angle would result in an acceleration of 0.25 g? Well, let's see. Let's make a free body diagram for the system. We're going to call this guy theta. Here's m. And here's m. So we're going to have a force over here, which is mg, right? Let's make this way positive, because the force over here is just going to be the parallel component of gravity, which is going to be mg times the sine of theta, right? And no matter what, this is going to be, this force has to be smaller than this, right? So we'll make that guy negative, okay? So I think that we can just do net force equals net force, right? So here we go. For the whole system, net force equals net force. So the mass of the system is 2m. We want the acceleration of the system to be 0.25 g. That's got to equal our force minus our force. All right? So it looks to me like mg, mg, mg cancels. So now I've got 2 times a quarter, which is what, a half? So 0.5 equals 1 minus sine of theta. So solidify this, and you get sine of theta is 0.5, and then inverse sine, you find out that theta is 30 degrees. All right? So that is that. I don't know why. I feel like these videos, I want your feedback on this, you guys. These videos, they need work. All right, so anyway, in the meantime, until I get something better, we're going to keep chugging along. All right, so here we go. All right, so here we go. So now we've got the same setup. This time the masses are not equal. All right, so it tells us that M1 is 5 times M2. So let's just call this M. No, try again. I did the same thing in my notes. I'm going to make, let's let M equal M2. And then with that in mind then, 5M is going to be M1, right? Okay, so we're going to call this M, we're going to call this 5M. All right, so there's our masses. All right. So let's make a free body diagram for the system, right? So over here, we're going to have our FG parallel, which is 5mg times the sine of 30 degrees. 5mg sine 30 degrees, okay? And over here, we've got our other block that has a massive m, so there's a force over here of mg. All right, so let's see. Now, it doesn't tell us what direction everything is accelerating in. It does tell us the acceleration. It tells us the acceleration is 0.1 g. I shouldn't make my g's like that. That's a g. There you go. But it doesn't tell us what direction it's in. So if we simplify this, this turns out to be 2.5 mg. And so if we assume that it began at rest, which I probably should have said explicitly, that means it's got to accelerate this way, right? So let's call this way positive and this way negative. So we're going to make this negative. And so we're trying to find our coefficient of friction. So kinetic friction, right? So here we go. It looks to me like, because like I said, this force is winning, the motion is going to be this way, which means my kinetic friction is going to go this way. All right, so let's see what we can do here. All right. Okay, so there's my drawing. So here we go. Net force equals net force. Net force equals net force. So mass times acceleration. So my total mass is 5m plus m is 6m times the acceleration, 0.1 g, equals, let's see, 2.5 mg minus my force of kinetic friction minus mg, right? So on this side, I'm looking at 0.6 mg equals 1.5 mg minus the force of kinetic friction. So let's see. This looks like if we solve it, we get the force of friction kinetic equals 0.9 mg. Yes. All right. So now to find the coefficient of friction, well, we need to go back to that block, right? So let's see. So here's the block. I already put in my FG parallel, but I didn't put in my FG perpendicular. So FG perpendicular is, well, this guy's a mass of 5m, right? So this is 5mg times the cosine of 30 degrees. So if you do 5 times the cosine of 30, you get 4.33 mg, which means then that my normal force is also 4.33 mg. And so, if the force of kinetic friction is the coefficient of kinetic friction times the normal force, then here's our force of kinetic friction, That's equal to our coefficient of kinetic friction times our normal force. Whoa, that is a weird looking 3, Mr. Hector. And solve it, right? So we can divide everything by 4.33 mg. And your coefficient of kinetic friction ends up being, I have a mistake on my works, I don't have the answer written down, but it is 0.9 divided by 4.33, 0.208 is the coefficient of friction. There you go. I'm going to do something about these videos. Me doing examples like this is not helping you any. All right, so let's see if we can focus in class on what you guys are struggling with, and that will help me make videos for the future. All right? Videos for the future